When it comes to the constants of nature, we don't have any probability distribution. So if someone makes a statement like, it seems to be very unlikely that the constants of nature would just have exactly the values that we do have, that's a completely meaningless statement because we can't quantify this probability. So we'll continue with the question, was the universe made for us? To which I think the answer is no, for all we currently know. So first I think I have to put this question into context. Physicists, as I said, we don't really like to talk about life and so on. But in cosmology, we often talk about the preconditions for life. For example, carbon is often used as a precondition for life, but some of you may think maybe this is already too specific. At the very least, you'd need something like a sufficiently complex chemistry, or indeed the possibilities for any structures to form in the universe. And this is all not life in and by itself, but it's something that we believe to be necessary for life to ever come into being. And so the reason physicists talk about this question, like, was the universe especially made for us? Like, do we have a special place in this universe? Comes from the observation that for some slight changes to the constants of nature, it would not be possible for structures to even form. It would not be possible to form carbon or any kind of sufficiently large molecule. The most famous example may be the structure of the carbon nucleus, which is a prediction that was made by Fred Hoyle. So he figured out that for carbon to be produced in stars, the carbon nucleus had to have a particular structure, it had to have a particular resonance, and that was later actually discovered. So I think one way to look at this kind of prediction is to say that the observation that we ourselves exist is also an observation, and that is good for some things. For example, for the observation that it must be possible for stars to produce carbon. There are some other examples where some changes to properties of the constants of nature or nuclei and so on would eradicate life as we know it. A particularly simple to understand example is the cosmological constant. So the cosmological constant is that thing which makes the universe expand, or actually makes the expansion of the universe accelerate. So if the cosmological constant was very large, then it would basically immediately rip apart all the structures in the universe. So stars and galaxies could never form. This is if the value is positive. If the value is large and negative, so the absolute value is large, but the sign is negative, then the universe would immediately recollapse after the Big Bang. So again, there's no way that structures could have formed. So again, we see that just the observation that we exist, odd as this sounds, tells us something about the cosmological constant. It's a similar story for Newton's constant. So Newton's constant sets the strength of gravity. If gravity is too strong, then stars burn out too quickly, and so on and so forth. There are lots of books that have been written about this. I'm not going to go through the entire list of examples. They all basically work the same way. You take a particular constant of nature, you make a small change to it, you figure out what happens to all the physical processes that we know of, and then you figure out that some of the preconditions for life are no longer fulfilled. Which brings up the question, can this possibly be a coincidence? It looks as though making these small changes makes it appear very unlikely that our universe would have had just exactly the right values for the constants of nature so that life can exist. So there's a big problem with this argument, which is that if you're talking about the probability of something, you have to quantify this probability. So normally, when we talk about the probability of, say, throwing die, we have a probability distribution that, in principle, we can either derive from a model for the die, or we can just collect it by throwing die many times and collecting the data. So we know it's 1/6 for each of the different phases to come up. But when it comes to the constants of nature, we don't have any probability distribution. So if someone makes a statement like, it seems to be very unlikely that the constants of nature would just have exactly the values that we do have, that's a completely meaningless statement, because we can't quantify this probability. So it's not a scientific argument. You could certainly say, and people have made this argument based on Bayesian probabilities, I find it surprising that the values of the constants are so as to allow for the existence of life, and that's fine. You're free to find surprising whatever you want, but it's not a scientific argument. There is another issue with this argument, which is, for one, it's just wrong, and that may be it may come somewhat as a surprise, because some of those topics that we talk about in the foundations of physics, it seems that nothing ever changes. We've been talking about some of those things for hundreds of years, like determinism, indeterminism, nature of time, and so on. But this is an example where people have actually come up with new arguments. For example, they figured out that there are actually other combinations of the constants of nature that do seem to allow for the preconditions of life in some form, and those are not the same as in our universe. One example, as I just said, Hoyle figured out that the carbon nucleus should have a particular resonance, so as for carbon to be produced in stars, but there are other possibilities, other ways you can make this happen, and recently someone has come up with a different way to do it, where the constants of nature are not the ones that we have in our universe. There are also people who have argued that we actually don't really need what's called the weak nuclear force. So the weak nuclear force is one of the fundamental interactions that we know of. It's responsible, for example, for radioactive decay. And some people have argued that we actually don't need it to create all those structures that we see in the universe. They call this a universe without the weak force. And they say in such a universe you'd still be able to produce sufficiently complex chemical structures. So it just seems that it's just not the case that there's only one particular combination of those constants. I also think that part of the reason why physicists fall for this kind of argument, like the universe is really, really special and we need this exact combination of constants, is that they tend to think that complexity is rare. It takes something to create it, whereas I think it's exactly the opposite. Like, complexity is the thing that we generically get if we combine all those physical processes. And this is actually an argument which was made beautifully in Stuart Kauffman in his book At Home in the Universe. He basically says if you combine sufficiently many things and you just give it time, then complexity will come out of it. I think that physicists they're not familiar talking about complexity at all, so for them this kind of thinking is a little bit alien. But I believe if we understand better how complexity comes about and how chaos works and all that kind of thing, we'll probably find there are many other examples of combinations of constants of nature that would also give rise to preconditions for life. So I really think it's more likely to be the rule than the exception. So was the universe made for us? For we currently know. No. So let me come to these two copies of us exist. So this is really a question about the multiverse. And I would say That's an example of a question which is ascientific, to use the word from my friend Palmer, which he brought this up in an interview that I did with him, and I just took it and ran away with it. Okay, so again, I think I first have to explain why would someone even come up with this idea that copies of us exist. That sounds certainly a little bit weird, but that's because infinity is weird. So in this standard model of the universe that we currently use for cosmology, the universe is infinitely large. This, by the way, is also the case at the Big Bang. I know that a lot of people have this idea at the Big Bang the universe was kind of like a small ball, but that's not quite right. So in the standard cosmology, the universe is always infinitely large. What happens at the Big Bang is really that the energy density becomes infinitely large. So, but the thing with infinity is that if you have some kind of density fluctuations in this early universe, and you just go out all the way to infinity, then any kind of fluctuation will happen somewhere with probability 1. That's what infinity does to you. Now, our solar system, our galaxy, and you and I, everything we know, grew out of this early hot plasma in the universe with those small density fluctuations in them. So if you have an infinitely large universe, then those density fluctuations, they will repeat with arbitrarily small changes to them. So there would be a version of Earth that's exactly the same as ours in every detail, except that there was maybe one cosmic ray that didn't come down exactly the same way, and it didn't damage someone's DNA, and your neighbor is still alive, or something like this. So all those variations should actually exist in an infinitely large universe. But the problem is the speed of light is finite, and we cannot communicate with anything that's outside what's called our cosmological horizon. That's basically anything we can reach by sending signals with the speed of light or below. The problem being that since the expansion of the universe actually speeds up, it becomes more and more difficult to reach other galaxies. So they're receding faster than from us than we can possibly communicate with them. To make a long story short, the universe may be infinite, and it may have all those copies of us, but we'll never be able to find out because we can never interact with them. So there are no observations that can refute or confirm that these copies exist. This is one of the simplest version of what's sometimes called a multiverse. One can quibble of whether those are actually other multiverses. Another example is what's called eternal inflation. So inflation is one of those theories for the early universe that I was talking about. The idea is that there is a new field which fills the universe. This field is called the inflaton field. So, and this is the only thing that exists in the early universe, and there are quantum fluctuations in that field. And from those quantum fluctuations, there are bubbles created, and those bubbles expand and give rise to the universe around us. Now, the thing is that in this infinitely large space, there are lots of those fluctuations again, and those bubbles keep on popping out forever. So there's an infinite number of big bangs going on in this eternal inflation scenario, and they'll keep on going on into all eternity. There are several variations of this idea of eternal inflation. For example, in some of those little bubbles that pop out and grow into universes, the constants of nature could be a little bit different from the one that we have here. They could also be the same. If they are different, this is often called the landscape. You may have heard of this as the string theory landscape. So this is actually where the idea comes from. String theory seems to tell you that the constants of nature should come with all possible values, so you can combine this with this idea of eternal inflation, basically by distributing the different values of the constants over the different big bangs. This is called the multiverse, though again one can debate whether this is a particularly good term. Of course, if you take the word universe to mean all that exists, then by definition the multiverse doesn't exist, which is probably not what the people who used the term intended. But that's the way that it goes with nomenclature. It doesn't really always make sense. So also in this version of the multiverse, there should be copies of us in all those other Big Bangs. Again, the problem is, though, there are no observations that can refute or confirm that these copies exist, because we can't interact with them. Again, you'd have to be able to send signals faster than the speed of light, or to transport yourself faster than the speed of light to get into one of those other universes. There's a final version of this copy argument that I want to mention, which you may have heard of. That's the many words interpretation of quantum mechanics. So, as I said earlier, in quantum mechanics we have two different ingredients to the time evolution. We have the Schrödinger evolution, and then we have the measurement update. The measurement update is indeterministic in the standard interpretation of quantum mechanics. Now, in the many worlds interpretation, people say, well, actually, making a measurement does not collapse the wave function. Instead, what happens is that the universe splits each time you make a measurement. So if you measure the particle, say, let's take a simple example where a particle goes on a screen and you want to know, does it go left or does it go right? In a standard interpretation, you would say, well, I've measured it and now it's on the left side and that's the end of the story. In the many worlds interpretation, you would say, well, now I have two universes. One in which the particle went to the left side and the detector says it's on the left side, and one in which it went to the right side and the detector says it's on the right side. So now you have two universes. And this happens all the time everywhere. Like every time some kind of photon bumps into the wall, the universe splits. So there are lots of those universes. And there are copies of us in them. Because all those quantum events happen around us. They even happen in your brain. You know, they happen every time you turn on a lamp. It's not a rare event. So in the many worlds interpretation, copies of us are all over the place, and our lives pan out in all possible ways that they can pan out. And there are a lot of people in physics who actually really believe that this is what's going on. Again, the problem is, though, there are no observations that can refute or confirm that these copies exist, because it's one thing to say, okay, the universe splits and all possible outcomes of a measurement actually do happen in some universe. In our universe, we only see one outcome. And that's what we know. And so there's no way to ever figure out if those other outcomes are actually real, or what it doesn't even really make sense to speak of something being real if you can't observe it. The reason physicists, at least some of them, believe that these copies actually do exist is the same in all cases. They basically believe that because there are equations for it, it also has to be real. So they have a set of equations. They have some reason to believe that those equations are correct because they describe something that we observe. But then they jump one step further and say, therefore, I believe that everything which is in those equations is also real, even if I can't observe it. Now the problem is, that's not a notion of real anyone ever uses. You know, it doesn't really mean anything to say something is real if you can't interact with it, if you can't observe it. You can just assume that those mathematical structures are real, but this is an unnecessary hypothesis. You don't need it to describe anything we observe, because it pertains to those parts of the theory that we do not observe. And as I said earlier, we shouldn't use unnecessary hypotheses in our theories. That's just not allowed in science. So I think these multiverse arguments are not proper science. We can't tell if those copies are real, so we shouldn't assume that they are. But this doesn't mean that those copies are not real, because science also can tell you that they do not exist. Science doesn't really say anything about it. So if you want to believe that there are copies of you out there somewhere in the multiverse, you can believe in this. There's nothing in science that speaks against it. This brings me to the last question. Can particles think? And you won't be surprised to hear that I think the answer is no. So again, I first have to explain why would someone have this idea to begin with. So this, I have to say, is maybe not so surprisingly not an idea that's particularly popular among particle physicists. It enjoys a certain popularity among philosophers. So they have this idea of panpsychism. Everything is a little bit conscious. Because it contains something that they call proto-consciousness. And the idea is that it explains where consciousness comes from, because you can combine all those little bits, very much like particle physics, and they form bigger things like us. And at some point, the proto-consciousness combines to what we normally call consciousness. Now, there are different variants of this argument. One is that this proto-consciousness isn't a physically real thing. So this is very much like dualism, and it doesn't have any observable consequences. So just like you can say, well, the mind and the body is really two separate things, and this is fine, you know, it's not in conflict with science. This idea of proto-consciousness without observable consequences is also not in conflict with science, but then, of course, you can't use it to actually explain what we observe, because it doesn't have any observable consequences. So that's really, I would say, a purely philosophical thing. But there are also some of those panpsychists, or whatever you want to call them, who think that this consciousness stuff is actually physically real. So they want to actually use it to explain consciousness in the old-fashioned scientific way. Now, the problem is that what you're doing then, if you're talking about the properties of the fundamental constituents of nature, you're actually doing physics. And then your talk about proto-consciousness better agrees with what we know about the fundamental laws of nature. So I have to look at this in a little bit more detail. This is what we know about the fundamental particles in the world. This is basically what everything is made of. Called the Standard Model of Particle Physics. You don't have to count them, there are 25 of them. Contains good old friends like the electron, and the photon, and the Higgs boson. The Standard Model of Particle Physics does not contain composite particles like protons and neutrons. Those are made up of quarks, each of them of 3 quarks. So the way that the Standard Model works is that each of those particles has a set of so-called quantum numbers, and the quantum numbers define exactly what the properties of the particles are. Quantum numbers, one that you're probably familiar with, is the electric charge. Some of those particles have an electric charge, sometimes it's negative, sometimes positive, sometimes it's 0. The particles can also have a spin. They have a property that's called the weak hypercharge. It's basically a more complicated version of the electric charge. The quarks also have a color, and so on and so forth. So there's this set of quantum numbers. And now the way that the Standard Model works is that you take all those quantum numbers for the particles, and then typically what you want to do is you want to calculate the results of some particle collision. And what you see in this picture here, this is what happens if you slam 2 protons into each other. So this is an image from Atlas at CERN. So the beams go into the screen, basically, and they run into each other, and then you create a lot of new particles, basically from the energy in the beams, and they go out and go into different kinds of detectors. And then what they do is they take the measurements in the detectors and they reconstruct where the particles came from and what kind of particles there were. And you compare this with predictions. So you have your data, and you make a calculation for what you expect with the standard model, and that's where the quantum numbers go in. And now the thing is, if there were any other quantum numbers that those particles had, then the results would just be different. Loosely speaking, it's because in quantum mechanics, everything that can happen does happen. So if there were more quantum numbers, then all those different possible values for the quantum numbers would also be produced, and there'd be more particles. And we don't see that. So if elementary particles had any other internal states than the quantum numbers, that just wouldn't agree with observation. So you can't just say, well, I believe that particles have an additional new property, which I call proto-consciousness. It doesn't really matter what you call it. There isn't any such property. So proto-consciousness can only exist if it has no physical properties whatsoever, in which case it does not explain any observations. So panpsychism is popular among some philosophers. So I should probably add that I'm not opposed to philosophy. In fact, I think physicists are not paying enough attention to philosophy. In some aspects, it'd be really, really important. For example, when it comes to the question, are those other universes real? This is really a question where you have to pay attention to what you actually mean by something being real. But the idea that particles have additional physical properties, whether you call these additional properties proto-consciousness or something else, is a statement about physics. So when philosophers start doing physics, then they actually have to pay attention to what the physics says. This is also, by the way, why I'm not a fan of the simulation hypothesis. This is another section in my new book. It suffers from the same problem. It makes big statements about the fundamental laws of nature without actually paying attention to what we know about the fundamental laws of nature. So do particles think? No. I think the overall story that I want to tell with my book is that I think science and religion aren't at war. There are a lot of people who try to play those two out against each other, but if you look at what's actually going on in the foundations of physics, then many of the ideas that physicists consider there, especially about the question how the universe began, they're basically extensions of some of those originally religious or spiritual ideas. They're just formulated in the form of mathematics. And there are many of those religious ideas which are still compatible with all we currently know. There are also some things that may forever remain unknown. I already said I believe that ultimately we probably won't be able to figure out how the universe began, because it seems to me that this is just a way that science is fundamentally limited, that we aren't allowed to make a story more complicated. Though that may not be wrong. Like, there may have been a more complicated universe before ours. It's just that the way that science works, we would never be able to say whether it was actually correct. Another question to which we may never find an answer is if there's actually a theory of everything. So this isn't something which I talked about here in any length. Again, that's something that I talk about in my book. But to make a long story short, the problem is there will always remain the question for any theory, why this theory? We know that the universe has to be in some particular way. I mean, we know that it is some particular way and not any other. So we need a theory that agrees with what we observe. But then there will always be questions in this theory which we can only answer by saying, because it describes what we observe. So I think this is another way that science is fundamentally limited. Scientists don't always mind this gap. I think some of the examples that I gave you show this very clearly, that sometimes they stray over into a realm where actually the methods of science fail, and they don't always notice. Okay, so this brings me back to my book, so I'm pretty much done. I hope you enjoyed this little talk. There are more questions in my book, and you can find more information on my website, existentialphysics.com. Thank you for your attention.
For more debates, talks, and interviews, subscribe today to the Institute of Art and Ideas at IAI TV.